Alright everybody, what's up? We got a good video this time. The definite integral. Alright, so let's go ahead and get started. So it says the definition of a definite integral is if f is a function defined between a and b, where x is between a and b, we divide the interval AB into n subintervals of equal width. And that width is, we'll call it delta x. And that is, and I wrote that wrong, that should be b minus a over n. We let x naught, which is a, x1, x2, all the way to xn, which is b, be the endpoints of these subintervals, and we let x star sub 1 all the way to x star sub n be any sample points in subintervals. So x star sub I lies in the ith subinterval, x sub I minus 1 to x sub I. Then the definite integral of f from a to b is, it's the integral from a to b of f of x dx is equal to the limit as n goes to infinity, where n, that's how many subintervals you have, is the limit of the sum of I equals 1 to n of f of x star sub I times delta x. And we're actually going to work a problem, an example where we use this to calculate the integral, provided that this limit exists and gives the same value for all possible choices of sample points. If it does exist, we say that f is integrable on AB. All right, and like I said, we're going to work an example where we find the integral using this limit here. So in the notation, the integral a to b of f of x dx, f of x is called the integrand. A and b are called limits of integration. A is your lower limit and b is your upper limit. And for right now, dx has no meaning. In other words, this integral here could be in terms of t. It could be f of t dt, f of r dr, and so on. All right, and the sum, this sum here, is called a Riemann sum. All right, so let's look at this right here. We've got these two graphs with areas, okay? And so if f takes on both positive and negative values, like in this figure here, okay, so we got positive values here and negative values right here, then the Riemann sum is the sum of the areas of the rectangles that lie above the x-axis and the negatives of the areas of the rectangles that lie below the x-axis. And the areas, these areas up here are positive, these areas down here, this area here is positive, this area is positive, and this area here is negative. And when we take the limit of these Riemann sums, we get this right here. Okay, we get this area here. See, this over here, these are finding areas using rectangles, but we can get this exact area here, here, and here. Okay. A definite integral can be interpreted. Okay, a definite integral right here, this right here, can be interpreted as a net area. That's a difference of areas. So you could actually, and what they're talking about here is the integral a to b f of x dx equals, say, area 1 minus area 2, okay, where A1, area 1, is the area of the region above the x-axis and below the graph of f, And A2 is the area of the region below the x-axis and above the graph of f. So what they're talking about here, and it's not necessarily these graphs here when I'm talking about A1 and A2, but they're talking about A1 would be like above the x-axis but below the graph, and area A2 would be below the x-axis but above the graph. That's what they mean there. Okay. And then we have a theorem here. If f is integrable on AB, then the integral f of x dx from a to b is the limit as n goes to infinity. And once again, n, that's the number of subintervals. I is the sum of, why did I write n equals I? That should be I equals 1 to n of f of x sub I delta x, where delta x is b minus a over n. That's the width of your rectangle. And x sub I is a plus I times delta x. And like I said, we'll work an example in a little bit on that. All right, so let's look at this example. It says express this right here, okay? Express this as an integral on the interval 0 to pi. All right, so all we're doing here is we're going from this form to this form. And so all that is the integral 0 to pi and our function f of x. See, there's f of x. So that's going to be x cubed plus x sine x dx. And that's all they're wanting there. Okay. So, it's a simple problem. It's not bad at all. And this is what they're wanting. All right. So formulas for sums of powers of positive integers. Now, we're going to actually use these later on. So formulas for sums of powers of positive integers. So the sum of I equals 1 to n, is n times n plus 1 over 2. And the sum for I squared is n times, and this should be, I guess I was in a hurry when I was copying all this down. And the sum of I squared is n times n plus 1 times 2n plus 1 over 6. And the sum of I cubed is n times n plus 1 over 2. And that should be squared. All right. I'm glad I'm catching all these writing down mistakes I have. All right. So, you can actually prove these things, but we're not going to do that in this class. Okay. But yeah, we're gonna use these in a minute. All right. So rules for working with sigma notation. So if we sum a constant from I to n, that's just n times c. And then this one is telling us that if we have a constant term c, we can pull that outside of the summation. And this one, if we got the sum of a sub I plus or minus, it doesn't matter if you're adding or subtracting bi, then we can split them up. All right. All right, so now let's look at this example right here. So this is an object is moving along a path. Its velocity function is v of t is equal to negative t squared plus 5t plus 6. Estimate the distance traveled from time t equals 0 to t equal 3 using 3 1-hour time intervals. So we're going to break this up into 3 subintervals. So basically what we're going to do on this problem, we're going to use rectangles and we're going to sum those areas up. We're going to do left endpoints, right endpoints, and midpoints, and we're going to compare those results and see what we get. And then we're going to do this same problem and we are going to find the exact area. I mean, we're finding distance, estimate the distance traveled, but we know that we have a velocity function and a time function, and when we do velocity times time, that gives us the distance. So we're going to actually find the exact distance, the actual distance, using the definition that we just went over. So we're going to work this 4 different ways. All right, so first, let's use left endpoints. All right, so we're going to sketch the graph. So the graph of this is, and I'm not going to go into how to graph this thing, but if you graph it, it's going to look something like this. And we know this right here is 6. We know that. And how do we know that? Well, this is t equals 0. See, this is t and this is v of t. And when t is 0, we know we get 6. So we know that. And we're going to break this up into 3 rectangles, and we're using left endpoints. All right. And so we need delta. It's going to be delta t, not delta x, because we got t here, because we need what? We need the width of the rectangle, delta t. And remember, we're going from 0 to 3. So we get 3 minus 0 over 3, which equals 1. So this delta t is equal to 1. And I know you can do that in your head, but I'm writing it down so you can see it. I'm showing all my work, because if I don't, then I'll get a comment, well, how did you get that? And you're not showing everything. All right, so we know the width of each rectangle is 1. So this would be 1, and that would be 2. All right, so I'll go over and explain this problem a little more, the left endpoints of how we're getting the areas, and then when we do the right endpoints and the midpoints, I'll go through those a little faster. All right, but what I'm going to do right now is I'm going to write the function down right here so we can actually see it. Negative t squared plus 5t plus 6. There's our function. All right, so remember, the area of a rectangle is the width times the height, right? The width times the height. So I know the width on all of them are 1. Okay, we know that. But now I just need the height. So what's the height here? Well, we know it's 6, but how did we get it? Okay, so the height of the first rectangle, we get that by evaluating the function at 0. Because see, when I plug in for 0, that gives me this value right here. And then I will evaluate the function at 1, because then it's going to give me that height. And then I'll evaluate it at 2, and then it's going to give me that height. That's how we get the height. The y value is the height, right? So that's the distance from here to here, from here to here, from here to here is the y value. So v of 0, well, that's negative 1 squared plus 5 times, v of 0, not 1. 0 squared, 0 plus 6, which is 6. And then v of 1, and I'm not going to do all this work on all of them, just this one. Negative 1 squared plus 5 times 1 plus 6. And that is going to give me, what is that, 10? And then v of 2 is negative 2 squared plus 5 times 2 plus 6. And that's going to give me 12. Now don't mess up right here. This negative 1 squared is negative 1. The negative is not squared, just the 1 is. So 1 squared is 1, and then I've got the negative in front, so don't mess that up. So I get the distance is equal to the width of the rectangle times the height. That's this first rectangle. Plus the width of the rectangle times the height, which is 10. That's the area of this rectangle. Plus, and then the width of the rectangle times the height of the rectangle, which that is 12. This is the area of this rectangle. So the distance is 28. And did they give us... Okay, so they don't give us any units, so, whatever it is, feet, miles, whatever. Okay, this is the distance. And that is using left endpoints. Remember, we got 28 as an answer. Now, let's use right endpoints. All right, so I'm going to sketch the graph again. And we don't need to go through all that delta t. Remember, delta t is 1. We calculated it right here. Now I am going to write the function down again. All right. And so this is 0, 1, 2, 3. Now I'm using right endpoints. So that means I'm going to draw my rectangle from this side. All right. So once again, we know delta t is equal to 1. Now let's get the heights. So to get the height of this rectangle, that's v of 1. And I'm not going to show where I plug it in, which that's 10. And then the height of this rectangle, which is v of 2, which that is 12. And then the height of this rectangle, which is v of 3, that is 12. Yeah, kind of weird there. Both of them equal 12. I wonder what that means. Well, that means the vertex is probably right here. Okay. All right, so I have my heights here. So all I did is took the 1, 2, and 3, plugged it in here to get the heights of the rectangle. So the distance is equal to 1 times 10, that's the area of this rectangle, plus 1 times 12, that's the area of this rectangle, plus 1 times 12, which is the area of this rectangle. And so that distance is equal to 34. And there's your answer. All right, now let's look at using midpoints. All right, so once again, let's draw the graph. And we know this is 0, 1, 2, 3. We know the width is delta t. Okay. And let's write the function down. The width is delta t equals 1, and our function is v of t is negative t squared plus 5t plus 6. All right, well, we're using midpoints this time. So that means we go to the midpoint of the intervals. And so this is what our rectangles are going to look like this time. All right. Now, remember, we need to get the heights of these rectangles. So to get the height, that's right here. See, these are the heights. Here, let me do it in a different color. Here, here, and here, those are the heights. So we need to evaluate the function at the x values here, here, and here to give us these y values up here to get the heights. So we need the midpoint of each one of these intervals. So, well, we know that's a half, right? And how do we get the midpoint between two numbers? You add them up and divide by 2. So 1 plus 2 is 3. Half of that is 3 halves. Let me write that a little better. 2 plus 3 is 5. Divided by 2, that's 5 halves. All right. So now we have v of 1/2, and you know what? I'm not gonna spend the time of calculating that. You can plug it into your calculator and do it. So what I'll do is I'll just write the distance is equal to 1 times v of 1/2 plus 1 times v of 3 halves plus 1 times v of 5 halves. All right. So yes, you would have to plug 1/2 into the function to get whatever this number is. 3 halves into the function to get whatever this is. 5 halves into the function to get whatever that is. I've got confidence in you that you can do it. And when you plug all that into your calculator, you get 31.75. And that's the distance that we get. All right, so we've approximated the distances, and we've gotten different answers on everything. Look at that. On this one, when we did left endpoints, we got 28. When we did right endpoints, we got 34. And when we did midpoints, we got 31.75. So those are approximate answers. I wonder if any of them are exactly right. Okay, well, let's see. So now we want to use the definition, the integral a to b f of x dx is equal to the sum as is the limit as n goes to infinity of the sum of I equals 1 to n of f of x star sub I times delta x. All right, so let's see what we've got here. So we have the distance is equal to the limit as n goes to infinity of the sum of I equals 1 to n of v sub t star sub I times delta t. There's our actual distance right there. And let's go ahead and write down. Let's write down v of t is equal to negative t squared plus 5t plus 6. I'm just writing the function down again so we can see it. That's all. I'll probably write it down as we have to keep scrolling. I'll write it down so we can see it. So now what do we need? We need delta t. We need the width. So we've got delta t is what? 3 minus 0, because it's from time t equals 0 to t equal 3, right? Over, now how many intervals are we going to have? N, where n is going to infinity. You see that? N's going to infinity. Oh, look at that. We're going to have an infinite number of rectangles. That's going to give us the exact area there. All right. So we have x naught is equal to 0. Remember earlier in the definition? Do you remember that? X naught was what? Look. Where is it? It's somewhere. There we go. See right here, x naught is equal to a. And in this problem, a is what? 0. All right. All right, so let's go back down here. There we go. And then we have x1 is equal to what? 3 over n, right? 3 over n. And then we have x2 is equal to 6 over n, right? Because from 0, we go over 3n, and then we go over another 3n. 3n plus 3n is 6n. And then if we go over another n, we would have x3 is equal to 9 over n. And that is going all the way to what? And you might be asking yourself, and I don't know why, I guess I'm just used to x. That's going to be t. All the way to what? T sub I. So what is T sub I? T sub I, well, that would be what? 3 times I over n. See, I can use this formula. So when I is 1, 3 times 1 is 3 over n. When I is 2, 3 times 2 is 6 over n, and so on. All right? And so to get our distance, we can plug this in. See, we're evaluating it at T sub I, our function at T sub I. So that's going to be the limit as n goes to infinity, sum I equals 1 to n v of T sub I, which is what? 3i over n times what? Delta t. All right. All right, so I hope all this is making sense so far. All right. See, all I'm doing is plugging everything into here. And what? I got T sub I, 3i over n. All right, so again, let me write the function down so we can see it. All right, so this is going to be what? This is the limit as n goes to infinity. Sum I equals 1 to n of what? Well, negative 3i over n squared plus 5 times 3i over n plus 6. Okay. How did I get that? How did I get that? Well, I'm doing what? V of 3i over n. So 3i over n, that's t. So I'm plugging 3i over n in for t. All right. And then that's times what? Times delta t. What's delta t? That's 3 over n. See delta t up here? Well, that's 3 over n. And on this one, I guess instead of writing delta t, I could have written 3 over n. I mean, I did plug it in there, so we might just put that as 3 over n, which is the delta t. All right, so now it's just a matter of simplifying this thing. So I've got the limit as n goes to infinity, sum I equals 1 to n of, what is that, negative 9i squared over, well, that's a squared over n squared plus 15i over n plus 6, and that is all times 3 over n. And now what I'm going to do is I'm going to take this 3 over n and I'm going to distribute it. And so that's going to be the limit as n goes to infinity, sum I equals 1 to n of negative 27i squared over n cubed plus 45i over n squared plus 18 over n. All right, so we're getting here now. All right, we're getting somewhere now. And so now, well, let's look and see what we have now. We've got the limit as n goes to infinity, sum I equals 1 to n, and that's going to be negative 27 over n cubed. Okay, remember, n in this summation, n is like your constant. Okay, so that's going to be times I squared. See, I is going from 1 to n. So times I squared, which that's going to be n times n plus 1 times 2n plus 1 over 6. See that? All right, where did that come from? Well, this right here is the sum as I equals 1 to n of I squared. So you remember that from, let me get back up here, right here. See that? That's sum of I squared. And then yes, we're going to have a sum of I also. So I'll use this. And then we'll also be using this one, C times N, for the last one. All right. All right, so let me erase that. And so that's going to be plus, and that's going to be 45 over n squared times, and then the sum of I is n times n plus 1 over 2 plus, and then the sum of this, remember 18 over n, that 18 over n is like C. So it's going to be C times n. Okay, remember that. Remember that property. Hopefully this whole video you've had your notebook out taking notes and you wrote all those down so you can just look up real quick at your notes. Okay. If you haven't been taking notes, start the whole video over again and start taking notes. I'm just picking. You can if you want to though. All right. So this is going to be the limit as n goes to infinity, sum I equals 1 to n. And what I'm going to do is, this is going to be what? Negative 9/2 times n plus 1 times 2n plus 1 over n cubed. Okay, so what did I do there? Okay, well, I brought the n cubed over here with all these n terms, and I brought the 6 out here, and 27 over 6 is 9/2. And then I'm going to do the same thing here. So that's going to be plus 45 over 2 times n plus 1 over n squared. And then here, this is just plus 18. The n's actually cancel out. And there you go. Now we can calculate the limit. Oh, I'm sorry. Look at that, what I did. That summation's gone. Because see, we did it. We did the headgummit. I did it there too, didn't I? All right. So, okay, so let me go back up here. Okay. So when I do the summation and I've got this I squared, the sum of I squared is this. That sum that I had written here, that's gone. Okay, because I calculated that sum. So it's gone. That's just, I guess I just got so excited working all these problems, it just slipped my mind. All right. So yeah, so the summations are gone. All right, so now we're ready to take the limits of these things. So let's take the limits. So the limit is going to be negative 9/2 times, okay, that's just a constant, so it's going to be that constant times whatever the limit of this is, which that's going to be 2. All right, so how in the world did we get that? Well, if you multiply this all out, what's your leading term going to be? It's going to be 2n cubed, right? And then you're going to have some other terms behind it, and that's going to be over n cubed. Okay, so if you multiply all this out, you're going to have 2n cubed as your first term, and then you're going to have something n squared, something else n maybe, and something else, and then, you know, maybe like, I don't know. But anyway, that's not important. Remember, when you're taking the limit as n goes to infinity, you keep the largest exponent from the numerator and the largest exponent from the denominator. And so this is the limit as n goes to infinity of 2, because the n cubes cancel out, which that's 2. All right, and that's going to be the same thing in the other ones too. But you know, you don't have to multiply it out. You just need what that first term, the largest exponent, is going to be. And it's going to be cubed, because see, we got n, and an n. There's 3 of them. So if you multiply n times n times n, that's n cubed. But well, we have a 2 here, so that's 2n cubed. Okay. All right. So now we've got plus 45 over 2. And then what's the limit of this? Well, that's the largest term is going to be n squared. That's going to be the leading term in the numerator, n squared. Well, n squared over n squared, that's 1. So the limit of 1 as n goes to infinity is 1. And then, of course, the limit of a constant term is 18. And so that is going to give us 31.5. And then whatever units it's in, miles, feet, or whatever. Okay, but that's the actual distance. So you can see, compared to those other methods, left endpoints, right endpoints, and midpoints, you can see they didn't give us the exact area, they approximated it, or exact distance, they approximated it. But the midpoints, it was the closest. I think that answer was 31.75, if I'm not mistaken. Okay. All right, so now let's look at some other problems. So we have the graph of f of x is this. This is your graph of f of x. And yes, this line here, that should be a straight line going through 2 here and hitting up here at 4. I drew it, so it's not drawn that good. And we want to evaluate these integrals here. So I want to evaluate this integral, and this function here, this is your f of x. This entire function here, that's the graph of f of x. So if I want the area under the curve from 0 to 2, well, I can see that is going to be 1/2, right, of 2 times 4, right? It's half the base times the height. The base is 2 and the height is 4. And so that's going to give me 4 as an answer. Okay, that's what they're wanting you to do here. And so what about this one? Well, it's going to be what? It's going to be half what? The base, what's the base? I'm going from 2 to 5, so the base is 3. And the height, it's down here at -2, so the height is 2. And remember what we talked about earlier, when the curve's above and below the x-axis, this is a negative. And so this is going to be -3. Okay, it's below the axis. All right. And so what about this one from 0 to 6? Well, if I'm going from 0 to 6, what I'm going to have to do is get this area plus this area plus this area. So I'm going to have to break this up into 3 different integrals. So this is going to be 0 to 2 f of x dx plus 2 to 5 f of x dx plus 5 to 6 f of x dx. Getting close to running off the screen. All right. And so this is going to give us what? Well, we already calculated the first one. See, we did that up here. And the second one. And then I've got to do this area. So that's going to be 1/2 times the base times the height, which in this case is 2. This goes all the way up to 2. And so that's going to give us 2 as an answer. All right. All right, so I hope that made sense. And we got one last thing to do. One last thing to do. And these are important here. These properties of the definite integral. Okay. So here, this is saying that the integral of c from a to b dx is just c times b minus a. That's c as a constant. Okay, it's a number. So if you have this, you're just taking that number times b minus a. And then this integral of f of x plus or minus g of x dx is this. This is just saying that you can integrate each term individually. Okay, just do each term individually. This one is telling us that we can take the constant. Okay, see, we're integrating with respect to x here, but we have a constant here, and we can pull that constant outside the integral. You'll use that a lot throughout calculus, pulling that constant out. And this one comes in handy too. The integral of f of x dx from a to b. So that's kind of like what we did in that example when we found that last one and we integrated all 3. We had 3 integrals, and that's what it's saying. See, if we have some number c that's between a and b, then we can split the integral up, a to c and then c to b if you need to. And see, that's what we had to do here. See, this is like going from a to b, but we had to split it up here and here. Okay, so you can do that. And you see that this is equal to this. All right. And then this one you'll use some. The integral f of x dx from b to a is equal to the negative integral f of x dx from a to b. So here, if you take the limits, see these limits here, and you swap them, it changes the sign in front of the integral. That's what that means. All right. All right, so let's look at this last example here. I know it's sad. It's the last example. I'm sure you're wanting to watch more. So it says if the integral f of x dx from 0 to 6 is equal to 10, and the integral f of x dx from 0 to 4 is equal to 7, they want us to find the integral f of x dx from 4 to 6. All right. So you can see let's look at these limits here that we have on our integrals. The biggest one we have is 0 to 6. Okay, that's the biggest one. So I'm going to write that 0 to 6 f of x dx is equal to, now I want to split that up. Okay, so if I'm going to split that up, look, I'm going from 0 to 6, and what do I have? I've got 2, 3, 4, 5, 6. See, here at 4, see, I've got something here on 4. So I'm going to split it right here. So that's going to equal the integral from 0 to 4, the integral 0 to 4 f of x dx, plus, and then the integral 4 to 6. Okay, the integral 4 to 6 f of x dx. And now let's just start plugging stuff in. So we know this is 10 equals what? 7 plus the integral 4 to 6 f of x dx. So that tells me that the integral f of x dx from 4 to 6 is equal to 10 minus 7, which is 3. And there's your answer. So I hope that all made sense. And hopefully you feel a lot smarter now. Okay? So that's the definite integral. So now in your calculus class, what you're fixing to get into is you're going to start learning how to integrate these things. You're going to start learning rules and stuff like that. And let me tell you, those rules are really important, especially the ones that you're fixing to get into. You really need to make sure that you understand how to integrate this stuff that you're looking at in this chapter. Okay? And I know in the Stewart book, this is the second section. The first section, I have a video on that. It's called Areas and Distances. You can watch that, and this is the second section. And then the rest of the chapter, I think for the most part, is teaching you how to integrate. And it's so important that you learn and understand how to do that, because if you learn and understand how to do that, then it's going to make your life a lot easier as you get on into the calculus classes. All right? So that's my little speech for the end. Okay? So I hope this video helped. Check out my other videos. Sorry about the screw-ups on some of those where I wrote stuff down wrong. I'm recording this video. It's 10 o'clock at night right now, but hope it helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see y'all in the next video. Later.